Today's speaker is Alan Ray, and his talk is titled Nanotechnology and the Real World. Alan Ray has worked in the electronics, ceramics, nanotechnology, and clean tech industries for over 25 years, both in the UK and in the US, managing global businesses and technology development at an operating company and corporate level. He currently runs TPF Enterprises LLC, a technology commercialization and consultancy company he founded in 2009. He holds director and VP position with 4 new companies. He's also the technical editor for Global Solar Technologies, a leading alternative energy publication, and is an entrepreneur in residence with NYSERDA, however you pronounce it.
Hi, sir. Okay.
Welcome.
Thank you. Well, good afternoon. I realize I'm the only thing between you and Friday beer, so I want to make sure that this is interesting. At the end of this talk, I hope you'll understand why nanotechnology is important not only to tennis balls, but also to flash memory, integrated circuits, even pens. So we're going to be talking about what is real life in terms of nanotechnology, where is it being applied. So, number of topics here. It's all about new materials. And why do we need new materials? Why can't we just make do with the materials that we've got already? What is nanotechnology and where did it come from? What can it do? Is it safe? Will it have an impact? What products are out there? And if you're working in this field, okay, how can I get involved? How do I start a nanotechnology company? And how do I get it to thrive and prosper? And what's next? Well, why do we need new materials? Well, if you're not working for something that's going to improve the human lot, you shouldn't be working on it, in my opinion. So in this case, we're looking at improving our access to food, water, and healthcare, to allow access to alternative energy sources, to conserve energy, and to replace or extend elements that are running short. Because those of us who learned the periodic table in chemistry may be surprised to know a significant number of these elements are running short. We're consuming them too fast. So these are key issues for the next 100 years. Let's talk about them and see what the scope is. The scope is basically sustainability. We've got to work towards developing a more sustainable system, and nanotechnology can help us to get there. So let's talk about food and water. In the New York Times today, there's a big article about the lawsuits against the EPA, who is trying to restrict the amount of fertilizer residues coming down rivers. Fertilizers and pesticide use are pretty widespread. They're in areas that you may not expect. I mean, if you're wearing your eco-sensitive cotton t-shirt, you may be surprised to know how much water is used in producing it, and also the fact that cotton uses 1/4 of the world's fertilizer and pesticides. So there's issues of cost, yield, water pollution. And then we have to freshen up the waters that really aren't suitable for use. And aquifers, most of the water, as you'll see later, that we can access is actually in aquifers. And in many areas, they're brackish, which means they're a little bit salty. The water may be polluted by agriculture, sewage, frack water, or indeed seawater is a major source of water. And this is where the water is actually distributed. And if you look at it, there's about 1% is actually accessible for use as fresh water. It's a surprisingly small amount. Rivers don't actually even qualify at 0.01%. It's a surprisingly small area. So we've got to find a way to clean up the water that we have, that we've polluted, as well as access the water that we can't get at. So let's talk about medicine. We've got a double dilemma. Developed countries can't afford to care for aging populations, and developing countries can't afford health care for their young populations. We get treatment-resistant organisms, and we need really low-cost, remote and targeted diagnostics and therapy tools. That's another big need for the future. Now, this eye chart here is the energy use. And by the way, this presentation is going to be accessible for you to refer to. And if you look at the energy use, you can see that Our biggest energy use here is petroleum, and most of that goes into transportation. Coal obviously goes into energy generation. Natural gas, which will be a bigger and bigger feature for the United States for the next 20, 30 years, is here. You've got geothermal, very small, wind, smaller, hydro, reasonably large, but with very little opportunity for expansion. Nuclear up here, and then solar power, very small at this stage. So there are lots of issues in terms of energy generation and energy consumption. And you'll notice that most of the energy, we actually throw away more energy than we actually use, thanks to Mr. Carnot and his cycle and other waste mechanisms that are out there. So where's the energy used? Well, these are Department of Energy figures, and you can see that in houses, you've got heating, cooling, water heating, lighting, etc. In transportation, most of it is light vehicles and heavy-duty road, and then everything else is relatively small. So we've got lighting, heating, cooling, industrial heating, infrastructure, transport, and communications. Now let's talk about the elements, and there's a really good article in this month's Royal Society of Chemistry News. The elements that are yellow have limited availability. The elements that are orange are really starting to be problems, and these are elements that are going to be critical for our future. Lithium, in terms of lithium batteries for rechargeable vehicles. Lithium is still the best available technology moving forward for battery systems. Indium, used in everything from solders to solar cells. But other elements that you wouldn't expect, like zinc, silver, hafnium. Hafnium is absolutely critical for the dielectrics that are used in semiconductor systems. And the whole rare earth group. Rare earth groups are critical for everything that you use. Neodymium is in every electronic capacitor. In every circuit that contains electronic capacitors, it's not in every capacitor. Europium and other materials are used in the amplifiers for fiber optics. So there are a lot of elements that are really starting to go short, and we need to think of other ways to do those same tasks. And again, nanotechnology is a way that we may be able to do that. For example, replacing indium by carbon, which is much more abundant. So what is nanotechnology and how do we do it? Well, the general description is that it's using materials with structures 100 nanometers or less, and this is the important part, where the small size imparts properties that are different than the bulk. And we'll talk about that. It's not just smaller, it's smaller and it does something different at the smaller scale. And the reason that you get these effects is because nanoparticles, you may have a couple of thousand atoms, and several hundred of these are on the surface. And as a result of this, they've got a higher energy, they're more reactive. And the other thing is that the physical properties can also be useful because these particles may be smaller than the wavelength of light. So you may get something that would be visible on a large scale, but transparent on a smaller scale. So how small is small? Well, this chart shows the a log scale here, where you can see here is 100 nanometers. So this is the kind of area that we're looking at. And about the size of a virus, a little bigger than DNA, below the wavelength of light, about 50 to 100 times smaller than a red blood cell. So we're talking fairly small structures here. We're talking significantly smaller than the MEMS structures that are fabricated in this building, or human hair, etc. So we're talking about really small materials. Well, where do you see them in daily use? Well, surprisingly often you'll find them in automobiles and things like car polish. There's a particularly nice polish called Eagle One that you can buy on the shelves of your local auto store. That contains nano wax. And the big advantage of that, from my point of view, is that it lasts for 3 months before you have to polish it again. You have tennis rackets, you have baseball bats, so lots of consumer products. Cosmetics is probably the largest use that you may be surprised about. Sporting goods, clothing, and we're starting to see it in construction materials such as self-cleaning windows. There's a lot of interest in medicine in terms of controlled release therapies, imaging therapies, and of course through all kinds of areas in electronics. So how you don't see nanotechnology, this is how it works on the car bumper. This is bumper rash on my wife's minivan. And it gets polished away. If you put polish in it, those of you that use car polish, you'll notice that when you polish it away, you get those white marks where the scratches were. That's because the particles of wax in there are larger than the wavelength of light, and you could see them. So if you use really small particles of wax, then you can't see them. So the scratches disappear. And guess what? The same technology is used in anti-wrinkle ointments. So the idea is that you fill your wrinkles. Those of you that are graduate students may have to wait a few years before worrying about this, but you fill your wrinkles with not wax grains, but fatty acids and other materials which are designed to have the right refractive index, and the particle size means that you don't see the lines anymore. This is big, big business. This one just came up last month. Airplanes. EasyJet in the UK has adopted this new coating called O, which they claim is a 39% reduction in drag. It's a spray-on coating about a micron thick, and there's about 113 grams of nanomaterial per plane. I guess this is probably either a silica or aluminum material, and they're using it to fill the microscopic cracks in the aluminum. Now, the 39% reduction in drag is a way oversimplification because there's different kinds of drags on an airplane. There's parasitic drag, there's surface drag, there's lift-induced drag, etc. But what's interesting is that what they say, 3-part process, surfaces are cleaned with oxalic acid. Oxalic acid is a great material for washing out of metal residues. It's what's in wheel cleaners. That basically forms the surface. It cleans the surface, gives it an anionic charge, which means it will track the particles of the emulsion. They go into the pores magnetically, well, that's not right, and held there while all the other protective chemicals have cross-linked, bonded, and cures. Now, the only thing I really don't like about this idea is the company that's doing it. The company is called Oops. And I'm not sure I'd want to have anything to do with an airplane that was treated with a company whose name was Oops. But that's another story. But in your cell phone, in your BlackBerry, your iPhone, your Android phone, these are the kind of applications that are in there. The scratch-resistant surfaces, anti-fingerprint surfaces, although those aren't working quite as well as we'd like yet. There are some color-changing textures out there, certainly in the displays, the antennas, and in terms of the structure. There are also some phones out there that contain antimicrobial silver so that you don't pick up bacteria from other people handling the phone. So, where are the products? The Woodrow Wilson Institute had a study going. I think it's just run out of funding, but this was the most recent set of figures that I got. So you can see that the biggest area of consumer nano products is health and fitness. That's kind of interesting. So that's your cosmetics. That's the things like the baseball bats and things like that. Automotive, significantly high. Every Mercedes that you see has nano silica in the clear coat. Every BMW has ultracapacitors in there that use nanomaterials for regenerative braking. So you can see that it's starting to get more widely used. Now, what are the elements that are used? Well, quite surprisingly, silver. Silver is a big item, and silver is used mainly because it's got antibacterial properties. You can often find it in things like pens, or if you look at the wherever you fly on a plane and the tray table is down and there's an advertisement, you have a look on there and you'll find that it's treated by Microban or another silver system. And what's quite funny is in order to get around EPA regulations, they all have a phrase that's like this one here that says, antibacterial technology is designed to protect the pen's surface and does not extend protection to skin. So by doing this, they've been able to get around the EPA regulations, but they're not going to be able to do that for long because EPA is changing that. The real problem with silver is there's about 500 tons of silver now going into everything from toothpaste to socks. And what happens with that silver when it ends up in our septic systems or our sewage treatment systems? It's antibacterial. Well, our systems work with bacteria. That could be a problem. The other ones, obviously, carbon is carbon nanotubes for reinforcement. Titanium and zinc. Well, the reason for titanium and zinc is for David Hasselhoff's nose protection. So, I mean, the good thing is that when they do remake Baywatch, A, it won't have David Hasselhoff, and B, the person that is there won't have to have a white nose, they'll have a transparent sunscreen. So how new is this? Well, we've been hearing about nano for a few years, but actually it's been around a lot longer. What really helped us in the nano industry was being able to see these things, because the big problem is, and we'll talk about this later, you can measure chemistry, you can measure properties above a micron. When you're around 100 nanometers, it's really difficult to measure it. So if you look at the sequence, it started in about the 70s. In fact, the original room at the bottom lecture was 1956, which was the first time nanotechnology was actually proposed. The Nanotechnology Research and Development Act was signed into law 2004. Current nanotechnology initiative funding for this year is $2.1 billion in the US alone. So it's a big business in universities and across industry. So let's go into a little bit more detail into some of the opportunities in these particular areas and what are the technologies that work. In food, water, and medicine, let's talk about water treatment. Water obviously is a big problem, and there are a number of ways to purify water. One is to use a filtration system that selectively attracts impurities. And this is a geopolymer foam. It's like a cement, but it uses sodium instead of calcium, and it's nanoporous. And what you can do is you can precipitate materials like iron oxide on the surface that will trap materials like arsenic. So this is some of the material here. So this is a very inexpensive way of trapping arsenic, which is a major problem in drinking waters. Selenium's a big problem out in California because of the evaporation of aquifer water that concentrates the selenium. You can also use these for reverse osmosis by making very, very thin and very, very high continuity membranes. Imaging is another area, and I understand that you're doing some work on this around here, but basically this is some work out at the University of Buffalo where they've been looking at using silica. Silica's got an advantage. Most of the quantum dot materials that are used to label are made of things like cadmium telluride. So your quantum dots may actually be more toxic to the organism than the disease that the organism's suffering from. But the great thing is this is an image done under infrared. So you can take a live animal, you can image the tumor or whatever you decide to attach the nanomaterials to by putting a hook on that will selectively attach to specific proteins. And you can do it while the creature is alive. You can do it in the process of operations so that physicians can actually look and scan the area if they've been doing cancer surgery to find out if there's any residual material there. This is a really great opportunity. So let's talk about energy generation and conservation. Well, with small size in electronics comes low power. So until you reach a limit, and that limit seems to be about 10 nanometers, the smaller you make electronic devices, the less power they use. And this is a 22 nanometer RAM from Toshiba. Intel Atom that goes in a lot of netbooks, that's at 14.5 nanometer. The next generation's 22 nanometer. We'll probably see one generation more in semiconductors. But once we get beyond 10 nanometers to 6 nanometers, we can't really follow the Moore's law process of just making it smaller. We're rattling up against quantum effects, electron tunneling, and we really can't take them smaller than that. So we've got to look for alternative solutions. Now, the electronics industry's been looking very hard at alternative solutions. If you notice your clock speeds on your computer, whenever you used to buy a laptop, it was sold on clock speed, 1 gigahertz, 2 gigahertz, 2.66 gigahertz. They don't do that anymore because it turns out that the faster you run it, the more power you use. So that's why they've moved to the multi-threading, where you have parallel processors that use a lot less energy. In fact, you're probably going to see laptops clock speeds going down to 1 gigahertz over the next few years, but with more parallel threads. We may see some similar ingenuity with semiconductors. Aerogels. This is another area that's nanoporous. If you've ever seen these materials, they look like solid smoke. And they basically are a very fine silica network. You can also make them out of carbon and other materials. You make a gel and let the solvent evaporate. And they were originally developed by NASA as micrometeorite traps, which are really useful in normal life. But in fact, one of the really nice applications for these that is being seriously considered is auto headliners. If your headliner is really well insulated, you can put a smaller air conditioner in the car. You can use less power. You can use less materials. And generally, it takes 1 pound of running gear to lift 1 pound of whatever it is you have in the car. So every extra pound you add actually adds 2 pounds because you have to have more weight in the suspension, the frame, etc. So this is an area that I've spent a fair amount of time in, is reducing the process temperature with nanometals. We all learn in analytical chemistry that melting points are absolute. Well, they're absolute until you get below about 30 nanometers. And then they start to reduce, and that's because the surface energy becomes higher, and you've basically got stored energy in the particles, so they'll melt at a lower temperature. So we've been working on this for solder applications, and the idea is to reduce the soldering temperature so that we don't damage the electronic gadgets, which, by the way, as you get smaller, they become more heat sensitive as well. So you've got a lot of trade-offs going on there. So this is a real application area, and in fact, the company that I'm working with is working on a project for nanosolder for power electronics. So this is what these layers actually look like. So this is these are silver nanoparticles, 300 nanometers, printed on. Hello. I hate it when it does that. So they're printed on paper. And in fact, I have one of these things here. This is printed. This is a battery. There's a nano silver circuit here, and on the end is an LED. And it's printed on a sticky label. And if you fold this over, the LED will light. You can't make a circuit easily on paper because those of you that are science fiction buffs will remember Fahrenheit 451. Fahrenheit 451 is just a little lower than the soldering temperature and the temperature that you could get silver or other materials to form a conductor. So putting it on paper all of a sudden starts to make this useful for point of use displays, displays on advertising, packaging, etc. Carbon nanotubes. We've all heard a lot about carbon nanotubes. It's basically a graphite rolled into a tube. You can make nanotubes out of molybdenum disulfide or just about any other platy material. And they're being used quite widely today in the alternative energy area. Siemens, for instance, is putting them in the carbon fiber boxes, structures of their wind turbines. And the reason for that is inside the blades is a box structure, which is really the structural strength. And in that you have epoxy, you have carbon fibers, and the weakest part is the epoxy that's holding the carbon fibers together. So you put much smaller fibers in there between the main fibers, which increases the strength quite significantly. So let's talk about scarce material replacement. Graphene's the other interesting form of graphite that's been developed in the last few years. And this is basically, instead of taking your graphite layers and rolling them up into carbon nanotubes, you just strip them off one at a time. So you can produce relatively large flakes, and you can actually do this. If you take a single crystal of graphite and put Scotch tape on it, you can actually rip single layers off. That's not a good production process. What you really want to do is separate these layers by intercalating chemically, then separate the layers, then reduce them. And then you can put them down onto surfaces by electrophoresis or other techniques. And it produces a really interesting conductive material. And it can replace indium tin oxide, which is the conductive material that's used on touch screens. It's used in every flat screen TV, every computer here. And there's an issue of supply of indium going forward. And what's nice about graphene is it really doesn't have any color, and you can trade off thickness. The thicker it is, the more conductive it is, the less transparent it is. So you can trade it off to get the kind of conductivity that you need. It's potentially very low cost. And there's a company, again, that I'm working with that's working on scaling up this process. Pretty interesting. So how are you going to use these things? How are you going to process them? How are you going to deal with them in your life? Well, how are they made? Basically, they're either made from a bottom-up process, which tends to produce very, very mono-sized particles, or a top-down process. And that can be milling, it can be spraying, or other techniques. But the top-down processes are lower cost, but they tend to produce a mixture of particles, whereas you can produce single-sized particles. In terms of assembling them into layers, you can take a leaf out of nature. Nobody put us all together. We self-assembled. And it's a very energy-efficient way of doing things. And there are some coatings and some structures that are now using the same kind of self-assembly processes that we start to see in nature. And what do these materials look like? Well, you can get spherical particles, you can get platelets, you can get fibers of various kinds. So there's a whole, if you like, there's a whole encyclopedia of different kinds of structures that you can use and different chemistries. So the next question is, okay, these things are new, are they safe? Well, it turns out that there are a lot of nanomaterials around us today. When you look on the Weather Channel, and you know when they come up and they say it's going to be a nice day, what's the pollution level, and it says find particulates. That's particulates less than 300 nanometers. And these are produced by plants, they're salt spray, they're dust, they're from forest fires on the other side of the country. So some of these are harmful and some of them are not. We use these materials today, carbon black and silicon tires, silica in milkshakes and M&Ms. We're using them in semiconductors, and we're breathing them in every day in diesel exhausts, unless you're following one of the blue tech vehicles that has a catalyst trap. So international government agencies are doing a lot of testing and setting policies that will hopefully, but not necessarily, be heeded by politicians. And again, there's an ISO group that's looking to harmonize the standards internationally. So why are people concerned about nanotechnology? Well, you can't see nanoparticles. If there's something that's going to hurt you, the worst type is something that you can't see. That's why people are so concerned about radiation or biological warfare. You can't see that you're being hurt until too late. You can't measure them easily. There isn't an easy way, a litmus test or whatever, to see that they're there. They're about the same size as many biological entities. And there is a potential for extended exposures in sunscreens and cosmetics and foods. So there's a difference between having nanomaterials in your iPod and having nanomaterials in your cosmetics that you're wearing every day. I would look very carefully at the ingredients on your cosmetics. There are some of them that purport themselves to be natural that are actually having quite high concentrations of nano-TiO2. That's not necessarily bad, but you should know about it. The toxicity results, by the way, are inconclusive. There was a lot of work done at the start of the nanotechnology revolution that people were really concerned about. But then they discovered, this was mainly on carbon nanotubes, that the carbon nanotubes they were using were contaminated by about 30% nickel, because nickel is the catalyst used in the manufacture. And what that meant was, one, they got wonderful results in using them for hydrogen storage. Well, guess what? Carbon nanotubes really don't work very well for hydrogen storage. And secondly, the nickel caused real problems with toxicity testing. So a lot of the science that's out there initially is just plain bad, and a lot of people are playing catch up to work out what is actually real and what isn't. So how do you manage it? Well, there are obviously ISO is really trying to stop the non-tariff barriers. The new regulations that are coming in Europe, which are well meant, the trouble is that they're different than the regulations that are in the rest of the world, and it's actually not worth a small company thinking of exporting stuff to Europe. Now, that's a non-tariff barrier, and the question is how to handle that, because the cost of compliance may be $100,000 per product. Tricky problem. So let's talk about the nanotechnology business. Suppose you've developed a new structural material or imaging material or therapeutic material. How do you go about turning it into money? Well, any technology goes through various stages. And if you can't read this from the back, this is hope, hype, disillusion, reality, and profitability. So what happened is, you know, the bill was signed about here where there was a lot of publicity. It went really well. Well, then we had a little bit of a financial crisis, which caused a shakeout of a significant number of companies and consolidation. And now we're starting to see people sell real products that are moving up the scale. Generally, the companies that are selling products aren't the companies that invented them. A lot of people have found that developing a new product and taking it right through to being a mass-marketed product is just so expensive and so difficult, you end up selling it to a GE or somebody else that can manage it. So, okay, so if you want to start a business, so let's talk about how do you get a good idea to do that. Well, first of all, you want to find a pain point that matches what the nanomaterials can do. And that'll really be determined by what you're working on, you know, where's your strengths, where are your opportunities, where's your skills. So maybe there's a material that's too weak. So you can think of nanotubes going into wind turbine blades. Maybe there's a material that's too soft. And the whole Mercedes issue was automobiles moved from solvent-based paints to water-based paints because obviously they wanted to reduce volatile emissions. Well, Mercedes realized they had a real disadvantage compared with BMW because there's a certain era of Mercedes paints where they just go dull like that. So they set the task of developing a paint that would withstand 10,000 car washes. And they did it. And basically, they worked with PPG, and they developed this really nice coating, which lasts very well. So if you see a Mercedes that's got a dull paint job, it's previous to this. Too visible, well, graphene can be used in conductive coatings to give you transparent conductive coatings. Too big, well, semiconductors, small is beautiful. Uses too much power. Reverse osmosis uses a huge amount of water, of electricity for compressing the water to go through the membrane. The nano foam structure I showed is a much cheaper alternative. Uses too much material. There's an additive system for cement that doubles the strength so that you can use half as much cement. And cement, by the way, is one of the biggest greenhouse gas contributors on the planet. Depending on who you talk to, it's between 7 and 11% of the greenhouse gas. You reduce the cement by half, you reduce the greenhouse gases by half. And then corrosion, surprisingly, if you put graphene on metals, and those of us who are chemists really find this cute, it short circuits the corrosion cells in the intergranular region. You wouldn't think it would work, but apparently it does. So you've discovered, okay, I want to develop nanotubes for wind turbines. Well, first of all, is it scalable? Can I scale this up? A lot of processes really aren't scalable. You've got to develop something that you can use standard industry equipment, pots and pans, the standard equipment that people use in order to produce it. Otherwise, it's going to be too expensive. You've got to have acceptable life cycle assessment. Some of the water treatment products, there's the issue of, okay, we've taken out the manganese from the water. What do we let go downstream? Are we going to create more of a problem than we started? You put silver in it to make it antimicrobial so that you can drink it. Well, again, what's going to happen when it goes right through to the sewer system? It's got to fit with the existing manufacturing infrastructure. Nobody's going to want a material that's going to need a completely different process to make a car or a tire or a window. They want something that's a really simple process. They won't stand something that's significantly different. And again, this is very important. I don't care what it is, I care what it does. I care that people can't see my wrinkles. I care that I don't have to polish the car every 3 months. I care that my doctor's going to be able to diagnose me more rapidly and cheaply. So how about handling these things? You know, these materials are very small, they're powders in many cases. How do you avoid inhaling them? Well, the fact is, they're almost never shipped as free powders. I visited one of the nanotube companies in Belgium, and they had plastic containers with 1 kilo of nanotubes in, which were that by that by that, because the bulk density is so low, because you can't compress them together. So you can't do that. You have to produce them either in a resin or a liquid, or in some way that they're incorporated. The other thing, of course, is once you dry them, in many cases, they've agglomerated. So all you've done, instead of creating very small particles of carbon, is you've created small particles of carbon that are very expensive and glommed back together again, so they're absolutely useless. The other thing that's interesting is when they've been processed, if you're looking at a solar cell that's had silver on, or this material here, it's no longer nano when it's been processed, because the particles have grown. So who regulates this stuff? Well, you've got the FDA and the EPA, and there are two specific rules that EPA uses. TSCA, which is the Toxic Substances Control Act, and FIFRA, which is the Federal Insecticides, Fungicides, and Rodenticides Act. And that's what they're using. If you're making any health claims, they'll get you under this unless you're registered. There was a company a couple of years ago was putting silver into computer mice and keyboards, and they got fined about $300,000 for not actually registering the product. States are looking at registering or collecting data, like Wisconsin, and then Cambridge, Mass, and Berkeley, California, have got reporting documents. They're not doing anything with it, but they're just asking you to report if you're using nanomaterials. So how do you measure them? This really gets to the big problem of, okay, so we want you to report your nanomaterials. Well, how about the nanomaterials that I've been using for years in tires? There's carbon black in tires that's nano-sized. Do I have to report the carbon black? Do I have to report the tires? So it's difficult to actually think about this. Now, all the regulations are looking at free nanoparticles, which are basically unconstrained ones. And what you find is, that there are really good analytical techniques on the fly that you can use for chemicals. There are really good techniques for bulk materials. But really, the only good way of analyzing these things is TEM, SEM, AFM. None of these are things that you can stick in your pocket. None of these are cheap. Well, AFM's cheapish. But it's not something that you can go and use as a litmus test to say, you have got too much material in the air. That's an issue. The other thing is the definition. And again, when you're writing regulations, well, you've got 3 distribution curves here. You've got a broad one. That's not very bright. You've got a very narrow one. So is it nano if all the particles are less than 100 nanometers? If the average is less? And what about the analytical methods? Because guess what? If you use SEM with one image analysis technique, you're going to get a different result than others. So actually analyzing these things is pretty fraught for the regulators. So if you're going to regulate it, you really need to know what it is. But that's really not important to people who use it, because you really are measuring what it does. So you're measuring what it does to the epoxy carbon fiber. You're measuring what it does in terms of imaging. So there's ongoing struggle, and it's going to last for years until people figure out, how are you going to analyze these things properly? Meanwhile, should you develop these products, or should you not develop them? A lot of people in Europe believe in what's called the precautionary principle, which basically means that you never want to use anything that might possibly hurt you. I'm paraphrasing it that. That's a complete point of view. The other point of view is completely unregulated Wild West. Well, we're somewhere in the middle. And that's going to need to be developed over the next few years. So how about sustainability? Are these things sustainable? Well, some of the processes that are out there really aren't sustainable. Some of the processes for making nanotubes are very high energy. Cadmium telluride is used in solar cells, thin film solar cells. And it's very interesting because people have been very concerned about cadmium going into the environment and to solar cells until somebody else pointed out that there's actually more cadmium produced by the coal-fired power stations that are generating the electricity that we are used to making the silicon solar cells, which have a much higher energy content. So cadmium, should you look at cadmium telluride as a bad thing or a good thing? Quantum dots. Many of the quantum dot processes, your yield is less than 5%. So is that sustainable? Can you recycle it? And again, we talked about the nano silver, which is a really nice, if you like, poster child for the challenges of commercializing nanomaterials. So you want to start a nano business after this. You've discovered something that isn't going to kill the fishes or mess up the sewage system. It's going to make the wind turbines better, and you want to do this. Well, where are the ideas? The ideas are in universities like this, and they attracted most of the funding in 2011. That's actually wrong. That's 2010. It's 2.1 billion in 2011. And most of this is channeled through National Science Foundation, Department of Energy, DOD, National Institutes of Health. And so that's one source. The other is individual inventors who are often associated with universities. And a lot of large companies have orphan inventions. And an orphan invention is basically, if you're somebody like GE, a business that's going to generate $5 million in 5 years isn't going to hack it. It's got to be something much bigger to make a difference to them. IP, intellectual property. You've got to develop something that's unique and protectable, and that's in terms of patents or trade secret. You have to make sure that nobody's going to get IP that's going to prevent you from running your business. And then you've got to identify a real need and potential customers. So you've got to have the ideas, you've got to have the IP, you've got to have the potential customers. So, if you're a big company or a small company, there are different challenges. If you're a big company, there's a lot of risk-averse behavior. And, you know, in the consulting field, I come across this a lot. You know, what if this doesn't work? Well, you move on to something else. But in a big company, that means I might get fired. So what big companies look at is buying small companies. And the interesting statistic is over 50%, and I've seen several studies that say it's 60 to 70%. Acquisitions are actually a lot more risky than people think. And again, you know, the new businesses, they're just too small to make an impact. But if you're a small company, it's tough to get in money, investment and credit. It's tough even to get companies to supply you. It's tough to attract people, and it's tough to learn all the pitfalls by experience. Well, let's talk a little bit about this. How do you get money? Well, if you're starting a small company, there's your Visa card to start off with, friends and family, hopefully we will stay friends and family after the exercise. Angel investors. Angel investors are hugely important to the industry right now because these are people who have high personal wealth, who look to invest in small companies in order to get a better return than they get from the stock market. And there are lots of consortiums that deal with this. There are over 40 of these consortia in the Boston area alone. Venture capital, the venture capital market is pretty much dead to this industry because of the fact that there isn't an exit strategy. There aren't IPOs happening very well at the moment. You can get money from licensees, and you can get people to buy you. In terms of revenue, these acronyms are all different types of government grants that you can go after, and that's a great way of getting revenue for the first few years. Commercial research contracts, likewise. Product sales, the most important thing to get to. License revenue, everybody thinks they'll be able to license it, but it's actually one of the hardest things out there. Certainly I've found that. So, you want to get really fast to product sales. And how much does it cost? Well, if you're looking at saying, okay, how am I going to do this? Am I going to finance this all on your Visa card? Well, it's only going to work if you've got a better credit limit than I have. Because to get a prototype going, it's going to be about $100,000 a year, in general. The product is, getting a product out is several million and 2 to 5 years. I talked to one of the guys from Procter & Gamble a couple of years back, and they budget between $45 and $50 million to put out a new soap powder. Now, the soap powder is something like an improved Tide, which is not a huge development. They already own the space on the supermarkets. And even putting that amount of money in, they reckon they've got a 50% hit rate. Qualification times are important. So you've got the material. So if you're making silver, you want somebody who's going to make it into an ink. You've got somebody who wants to put it on a paper label. And then you've got the people that buy the paper labels. So you've got all of these people need to qualify the product, and that all takes time and money. The other thing is, as a small company, you can't afford to create a sales channel, you can't afford to create manufacturing, so you find people who have these things and partner with them. So I'm actually involved in 4 startups at the moment, one of which is mine, which is the TPF, and I'm spinning off, I'm working on spinning off technology from Purdue and individual inventors, doing product development and helping to fund that by consulting. It's a Visa card company. It's got income from consulting and SBIR, and at the moment we're going for angel funding to commercialize a nano cement development. I'm also involved in a graphene company, spin-off from UB, and that's got SBR and state funding, and that's starting to take off quite nicely. This company here is an individual inventor who's developed a way of purifying industrial water. That's going to be a huge success for frack water, ethanol production, etc. So we're making our first sales, and the results are looking really promising. And then there's a company in Florida that's in electronic materials. Again, an individual inventor, angel funded, just looking to go to their second round of funding. They're getting promising results. They've got customers testing the product and say, hey, if this really works, we want it. So what are the lessons I've learned, or are there any lessons that I've learned that I can give to you? Most important one, surround yourself with people that you can trust. There are so many of these new ventures that I've seen that have ended up in court, or the partners fighting over well, I introduced you to this person, so I need to get a bigger share of the company than that. So working with people you can trust. You need to be able to trust your subcontractors. You need to be able to trust your customers. You need to find the right people to work with. It's all about the people. And if you don't get anything else from this presentation, please remember that one. The other thing is Bootstrap Buy Cheap. I'm at the moment moving into an incubator at the University of Buffalo. The people next door are moving out. I bought all the lab equipment at 5 cents on the dollar. It's a big advantage. Tap your state and federal systems. There's a lot of good incentives out there. People don't know about it. It really helps to go. There are people there in the agencies whose job is to help you. There's a lot of good stuff out there in terms of incentives, either grants or tax rebates or all kinds of things. Universities and colleges, one of the best unsung resources that we have. There's all kinds of good stuff here. If you can partner with your university, it's a win-win. It's a win-win for the university. It's a win-win for the graduate students that you work with who you may be able to employ. It's a win-win for you because it helps you to access things that you could never afford, and it also gives you opportunity to test drive people who can be your employees. That's really, really important. If it ain't working, move on. Don't get hung up about it. Most things don't work out the way you think they're going to work out, but enough of them do that you're going to be successful. But you've got to move on. I think Henry Ford went bankrupt, 5 times before he was successful in the automobile business. So, never give up. And the other thing is, forget any ideas of a 40-hour week. It's not going to happen. You're going to end up working like a dog, and you'll find it's fun most of the time. Now, my nemesis is the accounting and the audits and dealing with the state employment people and that fun stuff, which I really don't enjoy. But the rest of it, I really do enjoy. So, lots of people to say thanks to. I won't go through them all. But a lot of people have helped me on this journey. And, if I can help other people, then that's something that would make me very satisfied. So that's it. Thank you very much. I'd love to answer questions if you have any.
Any questions from the audience? Go ahead.
You mentioned silver at the beginning of your talk and then towards the end. I think you said there was something like 50 tons of silver used.
500 tons of silver used in antimicrobial worldwide.
Is that actual silver?
Yes.
And what is nano silver?
It's just silver that's reduced to less than 100 nanometers in size. So people, for example, if you go to Korea, you can buy it in toothpaste. You can get it in socks. You can get it in pens. You can get it in... the biggest use in the US is actually in wound dressings. It's the material of choice for burn dressings or wound dressings in the medical area.
And so it uses part of that 500 tons a year.
Yes. Yeah, well, that's all nanosilver.
That's all nano.
That's all nanosilver. So a lot of it's being used worldwide.
Okay, so 500 tons of nano silver a year.
Yeah.
So in addition to that, there will be other uses for non-nano silver.
Yeah, there's big uses for silver in the electronics industry, jewelry, solar cells. They're using micron-sized silver.
I might be able to add a little.
Yep.
The total use of silver in the world, I think, now is about 20,000
Yeah, so it's a way bigger than the nano usage.
That sounds like an awful lot, but if you calculate it out, you put all of that silver, it's mined and processed each year.
Yeah, it's very dense.
I did have a question regarding electronics. A lot of rare materials and some of the materials in short supply that you mentioned go into making devices. Do you think that it will become economical ever to actually go and recycle that material or maybe perhaps disassemble printed circuit cards to use specific components?
Yes.
Or is it definitely a loss?
Well, that's a really interesting question. Talk about disassembling the circuit boards first. We've started an industry in disassembling circuit boards. The problem is the components that are being disassembled are turning up as counterfeit components. And they're finding their ways into aviation systems and medical systems. And I don't know if you'd like a capacitor that had been in a PlayStation in your pacemaker, but I certainly wouldn't. So there's that issue, the whole counterfeit issue. When you get beyond that, it's easy to recycle the metals. It used to be very economic to recycle circuit boards when they had a lot of gold in them. And people made good money from old telephone company switch circuits. The gold content's way down now. So if you look at it, the main use of the actual circuit board, the epoxy, the main value of that is smelting it to get the copper out of it, and then the epoxy, the best use of that is to generate heat, so you get the calorific value. It's a thermoset, so you can't melt it. There's a lot of interest with packages and boards. Can you make them out of thermoplastics so that you can recycle them? And there are liquid crystal polymers and other things that people are using. When you get to the materials like the hafnium in the semiconductors, the issue there is a lot's used. There are a lot of semiconductors, but the amount per semiconductor is vanishingly small. So it really all comes out down to economics. If the value is high, then it's worth recycling them. But chemically, it's not easy to do that because it's pretty well bound.
The corollary is that aren't industries involved in this type of recycling themselves very polluting? I'm thinking, for example, of recycling lead out of lead batteries, which has contaminated the soil with acid and all things like that.
Yes, I mean, you have to regulate it. I mean, there's a big problem, especially with, I think the Berne Convention was aimed at preventing disassembly of electronic devices in third world countries. But a lot of electronics are being shipped illicitly to Africa and China, where people are being harmed by disassembling them. That's a real problem. Yeah?
Yeah, I'm working with a counterfeiting problem, and we are marking electronic parts with DNA inks and so on. And I'm talking with somebody who has nano color chip.
Right.
That makes sense.
Yes, that will be a quantum dot device that is difficult to replicate. So yeah, that's a good application for the nano inks. Yeah, the DNA, if you like, the DNA on the components, that's going to become something that's very, very important. I work with one of my non-paying jobs is I'm director of research for INEMI, which is the Electronics Consortium, and especially the aerospace people in that organization are really interested in that kind of technology.
Thank you, Dr. Ray.